Hi, welcome to DFS Traversal, which is used to finding shortest path uh, for the given graph. It will visit all the nodes of a given graph systematically. It will work for directed and undirected graphs and also weighted and unweighted graphs. So here, when you are selecting the undirected graph, you can visit all the nodes from any vertex to other vertex, right? So but when you're selecting the directed graph, when you're selecting any vertex that should have the path to reach all other vertices in the given graph. So when you're selecting the B, you see there is no outgoing edges from the B, so you cannot move or have a path from B to other vertices. So when you are selecting the vertex as a source from the directed graph, we should select as a it should have path from this to all other vertices through any vertex in the given graph. Here we can use a stack for storing the vertices in the given graph. We can select any vertex as a starting point of the traversal and push that vertex into the stack. After pushing that selected vertex into stack, then we have to identify non-visited adjacent vertices. Then if you found any non-visited adjacent vertices to the selected vertex, then you can push that into the stack. Here we have to repeat this steps until no other vertices are left to visit from the selected vertices in the given graph, right? So if all are visited, if there is no adjacent vertices without visiting, then we have to go to uh, stack, right? We have to go back to stack and pop the element from top of the stack. Then we should check is there any element is unvisited. If there is no unvisited elements, then we can keep on pop the elements from the stack until stack becomes empty. Once stack becomes empty, then we can stop the algorithm. So here it will take the time complexity order of all the vertices to be visited with using some number of edges. So it will take order of v plus e as a time complexity. The problem statement has been given with 7 vertices and 8 edges. This is undirected graph. We should identify the shortest path to reach all the vertices in the given graph. So here we can create an array of total number of vertices in the given graph. So here I have created the array of vertices for given graph, and I have used one of the reference field. Is it connected or not connected? That means visited or not visited. As of now, nodes visited sequence is nil. So here the stack is empty because of beginning the process. Now we are selecting any vertex from the given graph, because undirected graph, which is the starting point of traversal. Then we are pushing that stack into pushing that vertex into the stack. Yes, now pushing into the vertex into stack. Then select that a mark a is connected. Yes, a is marked as a connected, and also it is the first node it is visited sequence. Then find any one of the non-visited adjacent vertex of a. Here a is having two vertices, adjacent vertices. Then from that we can select any one, but that should be non-visited adjacent vertex. Here non-visited adjacent vertex we are selecting as a b, that will be pushed into the stack. Then after pushing into the stack, we are marking that node as a visited, v in the sense visited. Then here which is marked as a connected in the visited list. So b is on top of the stack. Now we have to select the b. We should check is there any adjacent nodes for the b. Yes, b is having three adjacent nodes. So here you can select any one of the adjacent nodes. So here Yeah, A is also adjacent node because of a bidirectional arrow. So now, but we the A is already visited, so no need to select that. You can ignore it. But there is B, D, F all are there. You can select any one of the node. So here we are selecting the D is here. One of the node is unvisited, so it is pushed into the stack. Then after pushing into the stack, we are making that node as a visited. So we are making that node as a visited, so we are marking as a connected in the reference table. Then that is added as a visited sequence. Then again we are checking the adjacent node to the D, right, which is on the top of the stack. So for this we have to check the adjacent nodes here. Both nodes are there. Here this is the B, this one is here D, this one is E. So we are having B and E, but B is already visited, so we can select the E. So now E is non-visited adjacent node, which is pushing on top of the stack and marked as a visited node. And also here we are using the connected table for the reference, so it is also marked as a connected. Then search for the adjacent nodes for E. So here the E is available here, B, this is D. For E, two nodes are adjacent nodes, but both are visited, so we have to ignore that both. So if the nodes are if the E is not having any unvisited nodes, then we have to check, right, we have to check the top of the stack. So we have to pop this E from the top of the stack, because as per the procedure, E is not having any unvisited adjacent nodes. The B is also already visited, D is also already visited, so we cannot move from here. So we have to pop the element by go back, right? So go back and pop the vertex from stack. So we are popping the E from the stack. After pop up, the D is on top of the stack. So D is, again we are checking is there any unvisited nodes, but it is also not having any unvisited adjacent vertices. So again you have to go back by popping up the D, right? You pop up the D. After that, B is on top of the stack. So for B, we are checking is there any adjacent vertex not unvisited. So B is having three vertices as a adjacent vertices. One is A, and another one is E, another one is F. So here it is having F is the unvisited adjacent vertex, so we are pushing that F into the stack, mark that F as a connected and also visited nodes. So then from the F we have to identify, right, from the F, this is F, from the F we have to identify unvisited adjacent vertex. Then for the F, unvisited adjacent vertex are C. Here B also there, but it is already visited, so we have to ignore that. Okay, then we can select the C is pushing into the stack and mark as a visited, and here marked as a connected in the reference table, right? After pushing that C, we have to identify adjacent vertices to the scene. So adjacent vertices to the C is again F, A and G, but this A and F are already visited, so no need to push that, so we can ignore that F and A. So now we are pushing that G into the stack, so pushing that G into the stack, which is marked by top of the stack pointer. Now this is marked as a visited in the visited sequence and marked as a connected in the table, reference table. Then now find the adjacent nodes to the G. Unvisited adjacent node is G, but C is one of the adjacent node, but it is already visited, so it is not having any unvisited adjacent nodes. Okay, so what to do? We have to go back, right, pop up the G from stack. So we have to pop the vertex from the stack. So we have pop up, then check the C is also not having any adjacent vertices, so we have to go back. So go back in the sense we have to pop up the C from the stack. So we have to pop up the C from the stack. So repeatedly we have to check go back from the f is also not having any unvisited vertices, so which it will be after removing this, top will be pointed this one, so f is also not having unvisited vertex, so you have to pop this. After popping this, this is the top. Then here b is also, we have to check unvisited vertex, so this is also not having any unvisited vertices, so you have to pop this b. Then this is the top of the stack. Then again you have to go back here. A is checking, so A is here, the this is the edge not carried the traversal, so we are checking this, but C is already visited, so we have to ignore this path also. So now A is also has to be popped up. Then after popping up the A, there is no vertices available in the stack. The all the vertices are visited as per the given reference table. Stack also becomes empty, right? So now the traversal sequence is A B D, A B D E F C G. This is the shortest path for the given graph. Then we can stop the execution. Here the time complexity is for the given graph, the order of vertices plus edges, because we are checking all the vertices and also edges. So when you are using the adjacency list, order of v plus e, but when you are using the order adjacency matrix, you will get v by v number of vertices, v number of vertices in the row and column, so it will be order of v square, that is order of n square is the time complexity when you are using the adjacency matrix. The space complexity will be storing all the nodes into the memory, so it is order of n. Thanks for watching.